Welcome to Computer Vision Decoded, where we dive into the quickly evolving world of computer vision. And in today's episode, we're going to go over practical tips and tricks for 3D reconstruction from images in different environments, because no two environments are the same, and you might run into issues depending if you're inside, outside, in an urban environment, etc. So I hope you guys walk away from this episode with something that you can go use today and get better results. I'm Jonathan Stevens, joined by my co-host Jared Heinley, our PhD in computer vision science, and he will have the answers for us. Welcome, Jared.
Thank you.
All right. Well, I'm excited about this episode because the last one we talked about depth maps and there was some practical application there, but we didn't really talk about like how to go out and do something or what research there has been in running into issues. So I'm really excited about this specific episode, especially because you've seen a lot of data sets, you've worked with a lot of different environments. But before we dive into that, I just want to ask you, Jared, like what's been new in your world since our last episode?
Oh man, something I've been having fun with recently is just meeting people working on robotics. So my wife and I recently moved to Pittsburgh, and so I started going to different robotics networking events, and as follow-up to that, been meeting a bunch of students or researchers in the area, so CMU or otherwise. And so it's been a lot of fun learning about their research and their work and seeing how computer vision or machine learning plays a role in these very practical real-world applications, because that's a nice intersection with robotics. It's that marriage between the digital and the physical world, which is something I really love. I love working on computer vision for real-world tangible problems. And so robotics, it's been a lot of fun to go deep with a few students on that and learn what they've been doing. So that's been a lot of fun. And as a plug, we're here in Pittsburgh now. We're trying to grow a team. Our team is hiring right now, looking for mobile developers, web developers, and product designers. So if you're interested, reach out. We'd love to hear how you might contribute.
Yeah, I say on that note too, if you are in the area and you're not looking for one of those roles, but you are in computer vision, this is a good chance to network with Jared because he is local and has a wealth of knowledge here in this industry. So I think it's interesting you talk about the interesting marriage of computer vision and like a machine being able to perceive its environment for it to enact on it. I've noticed that a lot of researchers lately have been moving to this generative AI in computer vision scientists. And so it's interesting to see this split. You have people who are going towards creating things that never existed and maybe never matter, like they matter, but they might be making fun experiences versus people who are saying, I want to dive into the world where I'm going to sense the world around me and I'm going to make 3D model or identify objects and inform a machine. So it's interesting how, one area of research can radically split what they're doing.
Yeah.
So this episode should be good for people in robotics because depending where your robot is in, you have different situations. Yeah. Definitely. Well, any research projects you're into?
Oh man. I guess just thinking about robotics, I have been reading up on a few papers that touch on, now again, not recent papers. I'm looking back at some of the more historical literature, trying to see how people have leveraged various constraints to help the 3D reconstruction algorithms. And we might actually touch on this today in some of the discussion, but thinking about if your robotic has known, if your robot has known geometry, like, oh, it's a car driving through a street and that car is always at a constant elevation above the ground, you can use that information to help the reconstruction, or if there's other things that about how your robot, the possible ways in which the robot can move, if there's certain ways that it can or can't move, adding those in as constraints. It's been a lot of fun just to kind of see and think about some of these new things that I haven't thought about before, because I've always typically thought about, handheld moving cameras, where that camera could do something random each and every image, every frame. But with a robot, sometimes you end up with smoother, pre-programmed a little more constrained motion, which can create some difficulties as well as opportunities for computer vision.
Right. That makes sense. Someone holding a camera, they got a natural gait to their walk, which is different than perhaps one person to the next, but also they can put that camera above their head, down low, change the orientation versus perhaps a fixed camera sensor that is always a constant level in orientation.
Yeah.
There's a lot less to worry about, I guess, and you don't have to worry about the ambiguity of people.
Yeah.
All right.
Yeah.
Yeah.
What about you? I know. I know you. I always see you, Jonathan, post on LinkedIn about new things you've played and tried. Played with or tried. What's been fun for you?
I like to see the research papers that come out. There's a couple different sources. I'm always just check every couple of days. I get excited though when code is live. And a lot of code, I'll peek at the GitHub page and say, yeah, that's not gonna happen. it's either not well enough documented, or it requires maybe 8 H100 GPUs. Well, that's not going to happen unless you're running it in the server, or just sometimes I just look and say, this is probably going to be way more work for me to figure out how to get going. However, the latest one I picked up was SB raster, which is short for, I have to read it off my screen. It was sparse voxel rasterization, real-time high fidelity radiance field rendering. So basically a new method for radiance fields, and as you know me, I like anything to do with that because I think it's just visually interesting. And so instead of taking a bunch of 3D Gaussians to represent a scene, that you kind of order them and then have these transparency effects and being able to reproduce, it takes a sparse voxel grid of a scene. So I like to think of the Minecraft analogy of Minecraft is basically like a voxel grid representing an area, but it has a way to turn these voxels into smaller cubes to the point where they look more like indistinguishable features of a scene. And it's really smart because they have ways where they can make some areas denser, so more voxels, or less dense, and then that way they can optimize the scene. I don't know, like for me, it's like, oh, it looks good when you look at their paper. I know there's a level of cherry picking data sets. More often than not, there's always the same data set. Yep. And they'll say like, this one is fractionally better than the next. And so you're like, oh, that's progress. But so that one I was lucky because I had spun it up on my computer. I pulled the code, followed the instructions, and it worked the first try.
Oh, wow.
All the dependencies, nothing. And I did this while I was eating a sandwich. So give you an idea of the time it took. And then I trained the first scene, like Gaussian splatting usually takes 45 minutes. This one took 10 minutes. It rendered the fly through in like 40 seconds. So everything was so fast, which was exciting too. It's because it's just so much more efficient. The real-time renderer on my PC was doing like between 100 to 200 frames per second. So it was fast. But as I'm seeing in some technology, it's kind of like everyone's already built towards 3D GS. And now this is great. Maybe this is better. But now as more and more applications are already now natively using 3D GS, it's kind of like, well, this may be better, but I don't know if anyone's going to take the time to create a whole nother way to ingest and visualize a new method. So
yeah,
we'll see.
There is something to whatever technique has a good supporting tool set around it and can get some sort of established workflow or usage in a community, because then you get that momentum, and sometimes that momentum can be hard to beat, even if there's some other method that's incrementally better. If one of them sometimes had the better paper title, or the catchy name, that's the one that gets cited and used then, forward through history. So yeah. I remember as a grad student trying, playing games sometimes, trying to say, okay, what cool acronym can I make out of my paper? Or, is there some way we could make this more memorable? But yep.
There's some pretty good ones out there. Well, enough about that fun stuff. Let's just jump into then what we're here for. Let's learn. I'll learn something, I'm sure, today. Even though I've been doing this for, almost 12 years, I still learn something in each one of these episodes. So I'm just gonna pick a specific environment And then let's talk about the different sort of issues that you would run into. So let's just go to an outdoor urban environment. So maybe downtown Pittsburgh, maybe New York City, maybe London, just some sort of urban environment where you got lots of buildings, streetscapes, hardscapes, not as many probably trees. What's the problem with that? That sounds like a great place to capture images.
Oh yeah, yeah, no, absolutely, absolutely. And I love. It's going to be fun talking about some of these different things because computer vision is just a tool. Structure motion is just a tool. It really depends on what application are you applying it to. And that's why we're talking about these different environments because each environment is going to have its own subtleties or challenges or opportunities where you can modify those base tools or use them in specific ways in order to get the best results for your particular application. So I love outdoor urban environments. I spent a lot of my PhD thinking about urban environments because one of the challenges you encounter is repetitive and duplicate structure. So I'm thinking, a skyscraper where you've got that same window repeated over and over, both in, along the building as well as up, on the different floors, or famous architecture. I think Big Ben in London, the clock tower, where all four sides of that clock tower look essentially the same. Because we as humans, we like symmetry. We don't just make random stuff and put it on the side of buildings. We do. Sometimes there's art and there's an artistic sense to that, but we also really love symmetry. And so that symmetry and that repetition ends up causing problems for 3D reconstruction. Because 3D reconstruction, a lot of times, is it's a maximization problem. There's a greedy algorithm behind the scenes that's looking at two photos and asking what is in common between these two photos. And so most of the time, if I take a photo and I take a step to the right and I take another photo, it's going to have no problem matching those images. It's going to find, oh yeah, there was a car and there was a sidewalk and some signage and some lights and a building, and it's going to figure out how those two images match, no problem at all. But let's say I'm in London and I take a photo of the north side of the Big Ben Tower, and then I walk around and I take a photo of the south side of the Big Ben Tower, and then ask computer vision, hey, what's similar between these photos? It may see that this stuff has changed, but it's going to find a lot that's similar, and so it's going to conclude, well, hey, I found stuff that's similar. I'm going to give that back to you. I can compute that, yep, the camera didn't move much because I still see the exact same clock face or a clock face that looks similar enough. And all of a sudden, now that you've discovered these correspondences and you think that the north side of the tower and the south side of the tower have matched, it messes up your reconstruction. Because instead of now getting a nice, reconstruction goes the whole way around the tower, typically what will happen is you might end up with breakage, and half of the tower gets superimposed, rotated 180 degrees, superimposed on top of the other half, and so you get an incomplete reconstruction where two halves of the tower are combined into one. That's one way that it's broken. You get the same sort of effect, so that's sort of that duplicate structure, repetitive structure. If I have the same pattern over and over again, you can get this just massive collapse where 10 different instances of the same window all get combined into one, and so you end up with that incomplete reconstruction. There was a really fun example where I was dealing with photos from an entire city. I think I was looking, it was either like Berlin, Germany, where I was using crowdsourced, publicly available photo collections. So like tourist photos that people had uploaded and said, yep, here's, free for public use. And so I was analyzing one of these crowdsourced data sets and was starting to look at, the reconstructions and the connections. And I found all of a sudden that like 3 or 4 different famous landmarks had all been linked together. And I'm like, how is this possible? These are like completely opposite sides of the city. What is going on? So I opened up my debug visualization, looked at the camera graphs, tried to figure out, okay, well, what is the link that's combining these landmarks together? And here it was a tourist who was wearing the same patterned shirt in front of all of these landmarks. And so so that's what it had found. It had found like they were standing nice prominent in the middle of the photo with kind of the background, behind them, but it matched the background famous landmark with their photo, with their T-shirt, and it thought that all these things were linked together. It was amazing.
So to jump on that, that that's the question I have, I guess. Then when you're doing, I guess, is the right term for this when you're looking between photo to photo is feature matching? Like you're trying to
Correct.
match. Okay. So if something has like a lot of uniqueness to it, being a tiki shirt, whatever it is the guy's wearing or the person, does the feature matching algorithm want to find things that are just already unique in the scene? Or is it just kind of uniformly look for features across the whole image and doesn't weight it towards like, oh, that person's got a really unique shirt. We're going to really try to match to that.
Great question. There is some like so it's a bit of both. So typically you will extract features, so just 2D key points
Mm-hmm.
throughout an image. So one image you may extract 10,000 different unique points, or 10,000 points, each of which will be described by the local pixels that are nearby them. So they're kind of just local appearance, saying, oh, okay, so it might not be the entire shirt. That shirt could have had 100 or hundreds
Mm-hmm.
of features on it that describes kind of local color and texture and shading nearby it. Um, each of those features is going to try to find its best match in the other image. So there is this holistic, let's match every single feature from one image with all of the other features in the other image. And you don't really weight or try to bias towards things that are more unique. However, there is some standard filtering techniques, I'll say, that once you've found those matches, you will sometimes prune or ignore matches that were ambiguous. So sometimes you may have a feature in one image that says, well, I matched really closely with two features in the other image. I'm not sure which one it was, and so I ended up picking one. But you could say, well, because that was an ambiguous match and there was a close neighbor that looked similar, let's ignore that match because it's probably unreliable. And so that's one way that we can ignore those less unique matches. There's also a similar concept in image retrieval applications. So assume I have a big database of images and I provide a single image and I say, hey, what other images in my database match to this image, my query image? And there we absolutely use what you just described, so trying to have this weighting mechanism that says, oh, if I see this particular pattern on a shirt and nowhere in reality, nowhere else in my data set has that particular pattern appeared, that feature is a very strong feature. It's going to be weighted much higher so that if that feature occurs in some other image, it's going to say, yep, I'm very confident that that's a relevant image, and it's going to recall that from your database versus just, oh, here's a feature that was on the grass. And if, half of my data set has grass in it, then it's not a very useful feature.
That makes sense. So in this case, make sure you hire a good computer vision engineer so they know what to do. There's a lot to that, right?
Yeah,
It's your algorithm, the one you choose or how you weight it, can give you a lot of false positive matches or not. So, okay, so we have duplicate structures.
Yep.
Duplicate people. Imagine if you had twins and you had no, just thinking in general, that is something I don't think as a human we intuitively walk around thinking, wow, I see a lot of the exact same doorways that walk through.
Yeah.
A space.
Or signage. Like there was again, like at winter time, okay, great, up in my town they put up little winter banners with snowflakes on it. It's like, well, it's the same sign every city block. That's going to confuse computer vision. I saw this too in Paris. Like the lamp posts have a distinct design to them, and so throughout the city, it's that same style of lamppost, and so they all started matching to each other and causing confusion there.
Shoot, I mean, anywhere in a city would have the exact same stop sign, street lights. Yep. There's a lot of things that I'm sure are exactly the same because they're standardized to be the same.
Yeah. And then we haven't really touched on it here, but then there's a whole host of ways that you can try to account for this and compensate for it, ranging from the, I'll say, like the stop sign or the lamppost, where maybe it is just a small set of features. I say, I had 100 features that matched, but then there were 10,000 that didn't match. Yeah, that's not a confident match. And so you could ignore those sort of low ratio or just low number of matches, ignore matches when there's only a small amount. So that's sort of on one end of the spectrum, ranging to other methods where you do like global reasoning, looking at your entire web, entire graph of connectivity between the images, and hypothesized that, well, in part of my graph, I had really strong connectivity. I think all these images are connected. But then here's this random link on its own that thought these two images that should have been really far apart all of a sudden are linked, and you can try to reason over that to figure out these images haven't co-occurred with each other. They haven't really matched with each other through other transitive links. It's unlikely that this is a valid link, and you can penalize that or ignore it in the reconstruction. So there's a lot of research around it, ranging just from heuristics to geometry to even learning-based techniques to try to identify these effects.
Okay, this is going to be an issue that we see repeat in other environments. For lack of a better word, repetitive.
Yep.
You're going to see them indoors. You'll see them other places. So let's just talk about then when you run into a situation. We see this even with every point at stockpile reports. Indoors, more than anything, we'll see repetitive structures in these warehouse structures where the rafters or columns will repeat every 10 feet with corrugated steel between.
Yep.
So what do we do? What is a tip someone could take away for how to deal with these repetitive structures out there in the wild?
Yeah. So, start with the fancy technique. If you're a computer vision researcher, yes, there is open source code out there. I've got one on my I've got 2 different methods on my GitHub. Or maybe I only released one. I forget. But yeah, there are open source. There's other authors I know that have released their code. But that's probably a little out of reach. More practical examples could be to just be aware of that repetitive structure. So if you know that there's going to be, either there's the same, like you said, sign. It's the same sign appears multiple times in the environment you're scanning. Just try to make sure that any time that repetitive or that duplicate object is captured, that there's a lot more other stuff in the scene that has been captured. Because again, computer vision, I mentioned before, it's greedy. It means it's going to go after whatever's easiest. And so if in your image there was a tiny little duplicate object, but then the rest of the scene is unique and has been seen in many other images, it's going to latch on to the rest of the scene. It's going to latch on to that big stuff, and say, oh, that little stuff, it's going to ignore it. So don't zoom into every single stop sign that you see and have that stop sign fill your frame of your image. Make sure that it's a minor portion of the photo. And that's one convenient way to
That's
to
an
avoid
easy
it.
tip, right?
Yep.
Like capture wide. Yeah. I'm also a big fan of wide angle lenses, not fisheye, but if you're outside with a 10 millimeter prime lens, you're going to get more than just a stop sign. And if that's all you're getting, you're just doing it wrong.
Yeah.
But even a robot, though, you get this wide view. Hopefully there's some other uniqueness in that area.
Yeah. Wide views, sometimes 360 imagery can help, just getting that full perspective in. That'll make the visual appearance more unique and help the computer vision algorithms to latch on to what actually is the correct correspondence.
Yeah. I've seen people sometimes probably run into this problem on, let's say, like a photogrammetry forum on Reddit, or now there's a Gotcha and Splatty one I like to follow, where they're like, I don't understand why I'm getting problems with my getting like a sparse camera result, trying to figure out where those are. This may be the issue. And I do also like to point out, if you're using software like reality capture, I think Metashape, there's tools too where if you know that's the problem, then you can go in and create manual control points to say, this is a unique point in several different images, and now it's got more control to help keep those images where they're supposed to be.
Yep.
But the problem is some people don't even know that's an issue. So they get these collapsing results and have no idea that, maybe it's because I saw the same thing over and over. I saw like churches as a good example too.
Yeah.
If you're getting pictures and you're like kind of just looking high up and down at a bunch of church pews, well, they are typically exactly the same over and over. Things like that might be very repetitive.
Yeah. And that's a great example of the control points. We've done that internally. If I just need a quick and dirty, way to get a result, create those control points, or they're sometimes called tie points. So creating a manual tie point between photos.
I think a tie point is more what is the right term, but just saying, enforce some structure. Saying, no, these have to be tied on this one specific unique thing in the scene, and it'll help keep those.
And depending on what you're doing, like if you're not trying to reconstruct whatever that duplicate object was, like if you were scanning some foreground object and there happened to be repetition in the background and you didn't care about reconstructing the background, and you also have time on your hands, you can also just manually mask out, like just black out. Just like I edit the photo, make that background black, wherever that duplicate structure was, just black it out, so that way the computer vision algorithm won't be able to analyze the texture and detect that there was repetition, because it's just going to see black pixels and it's going to do nothing with that.
Yeah, I've also seen people take that strategy of masking using, now there's great machine learning tools with what's a good example? People are using, it's that comfy UI. There's some great solutions to that where it's pretty easy to just set it up, and it's using like segment anything or these different models. And you can say, like, even people, although that might be repetitive if they get in the way, you can say segment out all the people, segment out all the street signs, because it's kind of these open source libraries of known objects, and it does a good job then of masking those for you. And if you have 1,000 images, you're sitting there trying to mask
That's a
1,000
great point.
images.
Yeah.
But it's out there, and again, that might be somewhere between a computer vision engineer and a hobbyist.
Yep.
But as you're working your way up, there is tools. So, all right. So we got repetition. That's going to come up in multiple of these situations or environments. So we can cross that one off. What else do we see in an outdoor urban environment?
One other thing I'll touch on is glass. So if you're in an urban environment with buildings, you end up with glass. Glass is transparent. It's reflective. Both of things computer vision typically hates. If you're trying to build a 3D model and what you're reconstructing is transparent or changes appearance as you change your vantage point, with those reflections, you get a noisy, incomplete, messed up reconstruction a lot of times whenever there's that glass. So one trick I've seen people do is, and I think there was even a paper from UNC that did this, was to use machine learning to detect windows in the imagery, and then use those detections to then enforce that in the depth maps, and then the resulting 3D reconstruction, that you end up with a planar geometry there. So instead of letting the depth map try to estimate depths and end up with something that's noisy or incomplete or has holes, and then fusing that together into your final model, which then just makes even more noise, just detecting it at the get-go and saying, you know what, whenever we estimate the depth of this window, make sure it's flat, because glass is typically flat, and using that just as a constraint to help improve the quality of your final result. So again, kind of more a little research level tip, but that's a little trick that I've seen people play to help improve the quality of a difficult to reconstruct object.
Yeah, glass is going to get you. And I think that we can talk some other strategies later on, but it's like when you're outside, you can't just like, oh, we'll just cover the glass up. It's probably not your property. If you were maybe doing your own property, you could do something there, but you're at the whims of the glass. I've noticed that I've seen this more on indoor scans, because I don't do as many outdoor scans with a lot of glass, but like I did my bathroom one time. You got these large mirrors, and then the end result, I had a point cloud that was the same room duplicated. It mirrored on itself, and the mirror became a portal to the second version of the bathroom, a complete mirrored opposite, which I thought looked cool. Absolutely was wrong. I doubled my square footage of my bathroom in one scan. So, but in that occasion, I could have covered it up. I could have put painter's tape and some paper over it to do something, whatever you want to do. But
No, and that's exactly right. Yeah, you could cover it up to create some texture, create some pattern there. But do you want to go the physical route or the software route, digital or physical?
So that one is harder to give anyone a direct how do you get around it, except for maybe try to just avoid trying to reconstruct those big glass buildings to begin with. Especially you maybe get a point cloud where you can not put in any, you could probably extract all the noisy points from where the glass was. But when you get to then making a mesh, then you get these big holes too you got to deal with. So lots going on there.
Yeah, it's tricky.
All right, so let's go from outside to inside. Now I'm in an indoor urban environment. So I'm inside, and what?
A lot of the same problems you had outside carry to inside. So again, with that duplicate or repetitive structure, symmetry. There's symmetry outside buildings. There's symmetry inside buildings. You may
Mhm.
have the same, signs. Like if you're in a commercial setting, maybe there's signage on the walls with company logos or brands or directing you to the different floors or the elevator or whatever it may be. And so you may have the same sign in different locations throughout that building, and so you have to correct for that. Or just the repetition again. Maybe it's a bunch of the same office door, in a
Mhm.
hallway, and you have that same door over and over and over again. Um,
Oh, I can imagine office environments where you have that paneling ceiling
oh yeah, yeah,
that repeats is
yeah,
could be a nightmare. And
yep. Or like fake wood flooring that has the same, like vinyl flooring that has the
mhm.
same printed pattern, multiple times throughout the scene.
I
Um,
lived in this house for 5 years, and I think it took me 3, 4 years before I realized the entrance tile actually it's a pattern.
yep.
It's like there's enough unique pieces that have different texture or different look, but then one day I was like, wait, that tile and the tile over there are the same tile.
Yep.
They're all
Yep.
manufactured with a print. So
Yep. Yep.
yeah.
Yep.
Okay.
Yeah.
Uh,
So that's a challenge. We just talked about windows. Yeah, so seeing a window from the outside versus the inside, again, that could be a challenge. A neat trick I've seen there. This was a paper out of ETH Zurich where they did, I think it was called like indoor outdoor 3D reconstruction alignment. And then it was like using windows was their main point. And so the neat idea they had was they were trying to align 3D reconstructions, like the outside of a building to the inside of the building, which typically, may have similar geometry, but, it's going to be different because depending on the wall thickness,
mhm.
depending on if there's parts of the building you can't actually walk to and get to. So it's not just a simple point cloud alignment. You need to figure out, well, how does the inside of my building align with the outside? And so they used windows as constraints. So they had again, like a window machine learning model, window detection algorithm, find all the windows from the outside of the building, find all the windows from the inside of the building, triangulate their 3D positions, and then run a solver that says, okay, now that I have 3D positions for all my windows from inside and out, how can I best align those to maximize the number of windows that line up? And then once you find that, you can use that as your transform to get the two reconstructions into the same coordinate system. So I thought that was really
Wow.
creative, leveraging that. Uh,
Windows can be helpful. I have a friend who builds camper vans, and we 3D modeled his camper van on the inside and the outside, and we wanted the door to be closed in the final model, so you could go like indoors, but instead of keeping that door open and getting it all in one go, so we having the window, I was able to capture some of the inside from the outside,
nice.
and then I was able to then match geometry from the inside and the outside when I actually ended up having two different final output models and just merged them instead of trying to reconstruct one scene from two different sets of data. I did that, and it worked great.
Oh, that's brilliant. I mean, that's brilliant. Yeah, let's just
So
look through the window from the outside looking in to see what's inside and then step
if you
inside
had
and
enough
then
of that, I could merge the two data sets perfectly.
love it.
It worked. Yeah, it's funny as those are one of those things that doing enough scans, I kind of know what works and what didn't. And I had confidence to leave knowing this is going to work, but also not, I didn't actually come in thinking that's how I was going to figure this out. It was just,
Hmm.
I was like, let's just scan the outside first and figure this out. As I was walking by the window being, oh yeah, I can see directly inside for the front half of this. So yeah,
Yeah. Nice.
power.
Nice.
I think for Windows, for me, you didn't have this in our lineup, but I think as well as people who are going around an indoor environment and have windows are a very interesting use case where you can have a huge dynamic range of light because
Oh,
your
yeah.
inside of your building isn't typically nearly as bright. I don't think people take for granted how bright outside is. And
Yeah.
so just daylight coming through a window can absolutely throw havoc into your 3D reconstruction because the camera can't compensate, is having to change all sorts of settings internally to, all of a sudden compensate for that change in light. So I always tell people they want to do a room, it's better to turn on the internal lights inside that room and close the window blinds if they have any, or somehow cover that outdoor light, because just if the light is coming through on a sunny day, it can be a nightmare.
Yeah. No,
So
that's a great point. Yeah, you want to have that, uniform lighting.
control your
Um,
environment. Yep.
yeah. Yeah.
Uh,
Because digital cameras, yeah, they're great, but they're only so good. And that,
mhm.
like you said, the dynamic range, that really bright sunlight it can't compete. I mean, it's just going to, blow out anything that's in the
Yeah.
rest of the interior.
And that way you can set your compass, your all your camera settings to a like stable environment. And if you're walking around taking photos, all of a sudden your shutter speed and your
Yeah.
exposure compensate, everything's going to change. Your depth of field might be different. So if you can just aim for a steady lighting, you're going to have an easier time at
Yeah.
trying to
Yeah.
reconstruct things.
Yeah. No, that's a great point. That's a great point.
Yeah.
Yeah.
Um,
With the
what else?
lighting, and was thinking about, just walking through a room, another big challenge with interior urban settings is, I'll say, textureless surfaces. I'll say, like, a lot of times that's walls,
Mhm.
where that wall is a solid color, and there's not, not a texture, not a distinct pattern that jumps out that's able to latch onto. It's like, sure, okay, I've got a big, poster on the wall behind me, or canvas or whatever, but then the wall then is painted, some other off-white color, but then it's just a solid uniform color, and computer vision isn't going to know what to do with that. Or, I'd say, when I say computer vision, I mean, image-based 3D reconstruction using something like structure from motion or SLAM, simultaneous localization and
Mhm.
mapping. There's no unique features for it to latch onto. And so that's where, like we touched on earlier, just talking about a wide camera view. So if your goal is just to be able to recover, how did the camera move through the scene? You don't actually care about reconstructing those textureless walls. Then one way that you can overcome that is by just having that wide camera view, because that's going to open up what you can see within that limited space within the interior of the room, and you'll be able to actually pick up things. Oh, there's a desk, or there's furniture, or the floor, or paintings on the wall, or other artwork. There's unique features that can latch onto. So just trying to avoid having the camera see dominant plain wall, but having some other unique things in that field of view is really helpful. 360 imagery is amazing for interiors, because with a 360 camera, now you can get a view in all directions and latch on to anything that's unique to help recover your camera poses. So
Yeah,
that's really nice.
I like to think of it this way when I'm capturing a room. If I'm taking images and not like perhaps walking around taking a video, if I was to stand in that room and then someone handed me a picture from within that room, would I be able to identify where in that room that picture belongs? And if it's just a blank white wall, you might say, well, shoot, this could be any one of the walls in here. I don't know. So there's got to be something in there unique enough, and hopefully more than just a corner of something. So,
Yeah.
being able to localize yourself to that room by just looking at what that photo is, it's essential.
And that's a great point. A similar thing I've also thought about too is, or not thought about, I've heard is, can you look at a photo, just take a glance at a photo and then look away. And if you can remember what was in that photo or identify what was in that photo,
Ooh.
That's another, because sure, like if you handed me a photo and I'm going to match the little freckles of the paint and everything. No, that's not what we're talking about. It's like you take a glance at the photo and then you look away. Could you figure out where that was in the room?
That's
That's
even
sort of the
better.
level of quality of what computer vision is able to achieve. And so we've used that analogy before. I've heard that analogy before, talk about even machine learning, saying, can you look at a photo, and say, oh yeah, that was a dog or a cat, or, what was in that photo? It's that sometimes is a way to approximate sometimes what computer vision can do,
Mm-hmm.
really quickly.
That gets into repetitive structures too, because if I like had my eyes closed, opened them up, looked at this picture, and it's an open doorway, and I close them again, I might say, depending on where you're at, you might say, well, that could have been four different doorways. I don't know
Yeah,
which one. So
yeah,
because you're at repeats. Like, well, I know, yeah, it's a door, but there's many of those.
Yeah.
It's got not only have to have unique features, but you be unique beyond just that, I guess. If there's repetitive things within that environment.
Yeah. And
I like that.
for the listeners, yes, we are obviously glossing over a lot of things. There's different types of features that you could be using or different techniques, but yes, in the broadest strokes to help guarantee the best success, yeah, typically you want to avoid these just blank textureless walls.
Mm-hmm.
Taking a different path, where sometimes that can actually help is leveraging planar flat things as a constraint in your reconstruction. So this also applies to outdoor reconstructions, but it applies perhaps even more on indoors, where, like I said, we as humans, we like symmetry, we like repetition, we also like right angles. And so rooms that are rectangular, have perpendicular walls, you can use that as constraints in your reconstruction algorithm. So for instance, I've seen this a lot to mitigate drift in a reconstruction. So suppose I'm going and scanning, a hallway, and my reconstruction algorithm starts detecting that, oh wait, there's flat surfaces. These points that I'm triangulating in the scene that I'm reconstructing has some flat surface to it. And well, as I walk along and reconstruct more, by default, in a naive implementation, that reconstruction can start to drift. And so that straight, hallway that should have then had, perfectly 90-degree corridors intersecting it can start to bend and diverge away from those perfect flat walls. But if you add planar constraints to the reconstruction and start saying, well, that I've identified flat planes here, 10 feet further along, I found similar flat things that were also really, really close to the ones I found previously. Let me just enforce and say, nope, these have to be the same wall. This isn't a slightly curving corridor. It's more likely that it was just a flat, straight hallway. You can use that to bend back the reconstruction and have that carry forward. Typically, just to kind of behind the scenes look, typically that might be done as part of bundle adjustment, which is the process by which you refine that final 3D reconstruction, taking all the camera poses, taking the reconstructed geometry, and optimizing it. That's one easy way where you can add in these extra constraints to say that, these points, this geometry in the scene should be flat and should be straight or should be at right angles. And so that's a nice trick to help to keep your reconstructions sharp and
that's it's good to know there's, and I don't know if code's the right word, but there's different research out there. And so if you are building let's say, think robotics, anyone building robotic solutions should have some experts on their team, but just to even be aware, especially if you're getting into that there's perhaps something that you can do outside of your capture to enforce better rigid rules into how the results turn out.
Yeah. And just to touch on some of this robotics literature I was reading, one of the works was dealing with an autonomous robot that it was on as a wheeled robot, and so it would drive through environments. And because it was wheeled, didn't really have suspension. The camera was mounted at a fixed height above the ground, and so as long as you're driving on flat terrain, that camera was always a constant elevation above the ground. Well, then they used that as a constraint to also constrain drift. So I talked kind of about this, or I mentioned this drift where, that hallway ends up being curved. There's another kind of drift, which is scale drift, where maybe my hallway would stay straight, but it keeps getting bigger and bigger and bigger the more that I go. And instead of staying a constant, width or a constant size. Well, if you know that your camera is always at a fixed elevation above the ground, you can add that as a constraint in your bundle adjustment and reconstruction and say, nope, as this robot rolls around, make sure that the ground is always a fixed distance above that camera position. And that's another way you can constrain the scale and avoid scale drift. So I thought that was, again, nice creative use of computer vision and the environment to build a more robust application.
I mean, if we're going to talk about robotics, and this is less of the amateur and more of the professional, if you have a robot or smartphone or a different sensor with inertial, like an IMU or these different sensors on there too. I know you also have tricks to perhaps know where you are within a room because you have a good idea of the trajectory of that camera from other sensors that know I'm not just using cameras to figure out where I'm at, or images, not cameras, but say, okay, well, according to this other data, I moved that direction so many feet. So, so these images can't match to images that were repetitive 20 feet ago because we're not even in the same place. So I do know there's a lot of that in robotics that you can leverage.
Yeah, absolutely, absolutely. Yeah,
And
leveraging that, just known like leveraging the sensor fusion. Like if you have a SLAM system that is reconstructing the camera pose in real time, yeah, if it said, okay, I saw something, I saw this unique sign, unique something, and then the robot knows that it, yeah, like you said, it moved forward 10 feet, and then, oh wait, I think I'm back at the same point again because I see that same sign. Yeah, you can say, nope, avoid that. That must be a repetitive object because my
mhm.
wheels, or my sensors told me that I was going forward. I didn't get picked up and moved back or whatever it was.
Yeah, we
So,
have that huge advantage using smartphones as well to capture because
yep,
ARKit, I don't know AR Core, but I'm assuming they all have
does the exact same thing.
you
Yeah,
know, all these movement sensors within the different devices to know that we've moved, and there's
yeah,
no way that you're in the same spot. So that
yep,
again a shortcut.
yep.
All right. So okay. So inside's kind of a nightmare for a lot of things. Um, I mean, it tips in general too. You got a lot of occlusions. That's one tip I always talk to people about too. They're like, okay, what's the best way to capture a room for a 3D model? And the first question I think specifically for radiance fields too is how do you want to look at it later? Because you could
Mhm.
you could get thousands of photos just to do a small space to get every occlusion filled and everything, but do you need it? You know, kind of think about how you're going to use this data in the end and what is actually needed before you go spend all this extra time probably capturing images that will either not be needed or just creates more opportunity for you to take bad images and make mistakes. So, you know, think
Yeah,
about that because
yeah,
there's so
that's
many
great
ways you can
advice.
capture a room, but you know, it I'd say less is more usually because when someone tries to go and overdo it, for lack of better words, that's when they tend to make mistakes because they're trying to get the hardest to reach, hardest to view parts of a room
Yeah,
and
yeah,
outside.
yeah, yeah. Yeah, it kind of
No.
comes back, and it's that walking pattern, that camera motion. How are you moving the camera to try to capture that environment? I see a lot of times people when they first try to capture a room, they might just walk, stand in the center, and spin in place. And sure, you can have now captured all of that on video,
Hmm.
but from a reconstruction standpoint, that's the worst case scenario. When that camera stays still and you rotate it, there's no translation. There's no baseline, to use a word from our last episode, to say, we need that camera motion in order to actually triangulate depth. And so, yeah, having the careful camera motion. Again, I know we had a whole episode before talking about the best ways to move your camera in particular environments.
Hmm.
And so that's always, like you said, there, if someone's trying to reach over, behind the sofa, or move the camera into weird or hard to reach places. A lot of times you may end up violating some of those constraints and
Yeah.
end up with bad results.
So in your notes, you had mentioned careful walking patterns. This is what we're talking about, avoiding walking through places. Doorways.
Yep.
That is probably the hardest thing you can capture.
Yeah.
How do I get from one room to the next with a confined doorway? It makes me think about me mentioning how I captured the inside of a camper van from the outside.
Yep.
It's almost like you need to capture the next room to some degree from the current room you are in before you try to cross that threshold where you're gonna have not a lot of good views. Uh, that
I
correct
think that is
hypothesis?
perfect advice. That is perfect advice. Because in reconstruction, you want to maintain dense, long connections, between multiple images,
Hmm.
and so, yeah, if I'm walking down a hallway, I want to start angling my camera to look into that doorway that I'm about to enter so that I see the interior of that room, like you said, see the interior of that room even before I've stepped foot into it, and so that way I'm going to have these long connections and lots of matches compared to just walking down the hallway and all of a sudden, rotating, and boom, I'm in the door. It's like there can be so few images to have made that connection. It's going to be really easy for the computer vision to have a break there in the connections and end up with a broken or a misaligned reconstruction.
Okay. So hallways are also a disaster. They're like a long doorway.
Yep. Yep.
I know we have talked, if you go several episodes back, we talked about, like, again, some best practices for like camera motion. Like if I'm taking video specifically and I want to capture a hallway, and I see this time and time again. Someone will be capturing something and they will walk straight forward with the camera and the viewpoint is kind of fixed on a specific area. And they're like, great, I got the hallway. But reality is majority of the camera is just the exact same, the wall on the far end of the hallway getting closer and bigger, but nothing's changed. There's no parallax movement except for the fringes of the camera. So like, what's a good way to capture a hallway like that? You probably don't have a lot of features as well. Hopefully you have a lot of art or something up on the walls. Is it just trying to get this wide angle and kind of go down one way and try to get the other way? Is that how you would think about it?
Yeah, like either the wide angle where I can, really see to the sides and get good views of that. A lot of times, I may do it in two or multiple passes. Where if I'm walking down the hallway, maybe I'll walk close to the right side of the hallway, but then have my camera angled kind of to the left, so that I'm not looking straight ahead. So I'm not looking ahead in the direction of motion. I'm looking left to see the left side of the hallway as it moves by me. And so if I walk down the right side of the hallway, look left, I can do that. I may then kind of repeat the process, come back, and then walk down the left side of the hallway and look right. What can get tricky is if I want to try to capture the hallway from both directions, which you can. So I can do it like in 4 passes. So, walk from right to, right and left from one direction, and then right from left to the other direction. But you would need to have careful points perhaps along the way where you can tie those 2 walking directions together. So maybe kind of doing some orbits or some circles, so that you're seeing the same point on the wall, the same point in the hallway from both, I'll just say north and south, from both the north and the south. And so maybe I will do an arcing motion, looking at it from the north, and then arc around, look at it from the south, so that now I've, tied together that point of the wall from the 2 different walking directions.
Okay.
Yeah, it can be tricky, like you said. Hallways are just a big, long, extended doorway. But
Practice.
Yep.
Yeah. Okay, so I know we are already spent a lot of time on this episode, so I'm going to try to speed things along. So I guess we've talked about environments, so let's just quickly touch on some other, like, not necessarily environments, but object-centric things that are tough.
Yep.
Humans. I like humans. I mean, everyone's like, why when I scan my kid, it never looks great? Or why, they try to get that perfect 3D model of a human. Why is that tough?
Yeah, that's tough because humans, we move. It's
Well,
you tell someone to stand still, and there's inevitably going to be little muscle twitches or slight motion, which violates then a lot of the assumptions of 3D reconstruction. 3D reconstruction assumes that whatever you're reconstructing has remained perfectly static.
Yeah.
And so reconstructing a human body or a human or a person is difficult because a lot of times there is that motion. And so you can't find a rigid match, a static match between 2 images. Part of it's going to match, but then other parts not, the parts that moved. So that's a difficult challenge.
That's why whenever you see like sometimes someone will post like an amazing 3D model of a human, and I just know they had to do that in a volumetric capture setup where they
Absolutely.
had 120 cameras all taking photos in sync, because there's no way you're going to get that great of an output if you're just taking photos and walking around someone. Plus, we all have to breathe. I once did it. I once did it with someone who's really good at this, and they were like, "Hey, I'm going to take." Where they did one on me, I had a Navis VLX slam scanner. It's like a thing that goes over you, and I was like, "Oh, can you make a 3D model of me holding this?" And they've done lots of these. Like they know what they were doing, and they said take short, shallow breaths. And I never thought about that, but that did make a difference, because then your stomach's not going in and out and causing havoc on it. And I was like, oh, okay. And they also said relax, because when you tense, you actually move more than if you just kind of try to untense. So there's nothing magic there except for just trying. I mean, even when you're sleeping, you're breathing, so you're always moving.
Yeah. Try to stay still. Like, the camera rig, that's a great trick. We talked before about, with the duplicate repetitive structure, trying to mask out the background. Sometimes that can help too. As if the human is moving, computer vision may latch on to the static, non-moving background. And so if you use some semantic segmentation or background segmentation to remove those pixels and only have the human in the image to be reconstructed, well, then it kind of forces the computer vision to pay attention to the human, and it can help recover for some motion. But again, your mileage may vary.
Yeah. All right. So let's move to the next subject. So Jared just bought a brand new Lamborghini. No, he didn't, but let's just say he did, and he wanted to 3D model it. And of course, you have it highly polished, is shiny. Even cars that aren't washed every day, it's got some layer of shine. You got glass. We got all the classic things that we've talked about. The wheels repeat, I'm assuming. What is the headache there, and what is your solution?
Yep. I'm gonna go take it muddy. I'm gonna go off roading with it and get some dirt all over it. No, that's so a shiny reflective surface like a car is difficult to reconstruct, just like we said, with windows, shiny reflective, the repetitive structure of the wheels. As we said, there's a lot of challenges there. This is not usually an option, but if you can add texture to that surface, cover it in some dirt or mud or paint, that's a great way to help computer vision latch onto the texture. There are even, in the paint category, want to do something permanent. There is a category of scanning sprays that are designed to make reflective surface more matte. Now, this typically applies to, or I've seen it applied to LiDAR scanning, where LiDAR sending out that light, measuring the time of flight, or that distance comes back. If that surface is reflective, it can help. It can end up bouncing the light in different directions instead of returning it back to the receiver. And so there, if you use these scanning sprays, it's just a temporary covering, a temporary spray that just ends up on the surface, and then it dissolves or washes away after a few hours. That can make your surface matte. And so that can be a trick if you are using some sort of active depth sensor, structured light, time of flight sensor, LiDAR. We used the LiDAR sensor on iPhones, and having a matte surface can make that reconstruction process a lot easier, because
we're gonna plug Recon 3D is built on every, they use every point in there as their 3D reconstruction back end, and it's amazing. I mean, I've used that app to scan my car, but I remember when my brother-in-law got a brand new black Chevy Silverado. This thing was right off the dealership. I'm like, we got to do a model. And I mean, as shiny as it was, even the LiDAR sensor managed to come up with a really good surface. It didn't look great if you photo texture it, because again, like photo, the shine changes, but we got a great point cloud. Yeah. So that's something we don't really talking about, but if you're photo texturing things that are shiny, it's kind of a nightmare. A lot of times you almost need to get the geometry of it and then take it into some 3D modeling software and replace that texture with a made up texture, because you're never going to get it to turn out right.
No. Because the shiny objects, it has a view direction dependent appearance. So depending if you're looking at it head on from any different angle, the appearance of that object changes, because the light that you're seeing is not the color of the surface, it's what's been reflected to it from somewhere else in the scene. And so anytime your camera moves to a different angle with respect to that surface, you get a different appearance, which then you try to now stitch that appearance together into a nice cohesive phototextured mesh, and you end up with all sorts of weird artifacts.
Yeah. Okay, so I'm just going to talk about maybe a couple more things. We had a whole bunch of things about stockpiles. I don't know if anyone's going to be into stockpiles as we are. I mean, I've seen all kinds of problems with stockpiles. Usually the biggest problem, it has nothing to do with the stockpile itself, and it has to do with the fact that there's got a concave area. And people just do what you said earlier. They get to a point where they kind of walk into a corner and they just take a bunch of photos from one position, and that's a big no-no. So
Yeah,
nothing
yeah,
wrong with the environment except for just never walk yourself into a corner and then keep taking photos in one spot. Like just do a bunch of arcs around the corners. Uh,
yeah,
capture with your feet, not with your arms. So,
yeah.
uh,
I
yeah.
will just touch on that. I mean, I will just touch on stockpiles, and I think okay, it doesn't have to be stockpiles. It kind of generalizes more to just the natural environment, nature, the
Mhm.
outdoors, non-urban settings. Um, for my entire PhD, when I was dealing with photos, like, well, what photos do I have access to? A lot of it was urban environments. There was nice, newer construction where you had really crisp repetition and things like that. I also dealt with more ancient environments, the Roman ruins and the Colosseum and things like that, where yes, it is an urban environment, but because it's built out of rock and it's deteriorated over time, there's a lot of unique texture and patterns. But again, it's still in that kind of urban settings. You have planar geometry. You do have some repetition at
Mhm.
times with the newer construction that's popped up around it. So a lot of my background had been focused on urban environments, but when I was introduced and started working with stockpile reports and EveryPoint on this problem of outdoor industrial computer vision in these construction environments, I love stockpiles because stockpiles are not shiny. When I say stockpiles, think mulch, sand, gravel, piles of material that you've mined from the earth from a quarry, crushed it up into rock, and you've got a pile there sitting on the ground. Those piles are not shiny. They are not reflective. They are not transparent. They don't have repetitive patterns. You may think that, well, okay, it's a pile of rock or pile of sand. It's just going to look kind of like the same rock or sand. Like to a human, one patch of the pile may look the same as the other, but it's actually it is unique. That is
Mhm.
texture and pattern that the computer loves,
Like a
and
giant
so
QR code.
yeah,
we
exactly.
don't see that pattern,
We don't see it. We
most of the
can't
time it
comprehend
is.
it. Yeah, like I
Yeah.
think yeah, sure there is, large structure that we can perceive. We can see the crests and the ridges, and some of that rock's darker or lighter than the other, or there's water on it or something like that.
Mhm.
But no, the all the individual rocks in a patch of rocks has a unique appearance, and so computer vision just loves that.
Mhm.
So yeah, I've really come to appreciate and really enjoyed thinking about these outdoor environments and the new types of constraints that you can leverage. Whereas before, you know, some of the algorithms have to be really robust and take all these special precautions to try to account for repetitive structure, flat surfaces, shiny objects. Whereas when you're optimizing your application for an outdoor environment where these things aren't going to happen, you can accelerate and optimize certain parts of the reconstruction process. Or what you touched on before, you asked about feature matching, and oh yeah, do you have to take into account the uniqueness of the features? Well, if I know that every feature is going to be unique, I can sort of make some optimizations to accelerate the process and leverage that uniqueness to get better results. So it's a fun environment. At first, when I was like, I go from reconstructing famous landmarks to reconstructing dirt. What's the appeal in that? But as a computer vision scientist, I love piles of dirt.
Well, and they're not without their own, let's just generalize it to outdoor
Yes.
natural environments. There
Yep.
is still lack of texture. We still see like sand can be very,
Yep.
you
Fine,
like,
fine silica sand, silica
uh,
stuff like that. Yep.
I'm sure you see that in other outdoor natural landscapes. You'll see just some blank surfaces.
Blank surfaces, I would say also talking about the occlusions,
Hmm.
vegetation. Vegetation is really, really hard. Grass, trees, shrubs. I'm not talking about like tree trunks, but I'm saying anytime that you have leaves, where again, depending on how you move, one leaf is all of a sudden going to include the other leaf, or a blade of grass occludes the other blade of grass, and so it acts almost as if it were a shiny object. And you
Yep.
end up with this view-dependent appearance, and so that those parts of the scene can be hard to reconstruct.
So good one on the grass is there was a point in which I was trying to 3D model my backyard. We had put in brand new. I moved in this house that had just a dirt pit in the backyard. So we got all landscaped. We had brand new sod in there, and it looked great. And this is the time to capture it. And I remember capturing the grass and being like, why does it come out weird and doesn't look right? And I asked you questions, and you're like, let me think about this. And then I remember messaging you the next day saying, don't worry about it. It's all in how I captured it. And instead, what was happening was I was like capturing a ring around the grass. And I found that if I actually kept my camera pointed towards like one cardinal direction, I would always be seeing grass from one direction. And it like seeing grass from one side versus the other side, like east versus west, it looks completely different to a camera. So I realized I have to just be walking in looking one predominant direction when I'm doing these unique grassy features, or else it was saying like, wait a minute, the grass looks a lot different from 180-degree turn. Yeah, and so, you probably could have figured some fancy things out to help that, or you could just capture in a way that helps yourself.
Great point. That's a great point.
Another thing, not with stockpiles, but outdoors, is there's two different elements that we have to battle. One is wind, which moves objects. So your object, if it's not static, is not going to maybe either not reproduce or might duplicate, or all kinds of crazy things happen. And then another one people don't think about, I think about this one doing like NERF or 3D GS capture, because it's so view dependent in your output, is that if you're out in a bright sunny day and you have strong shadows, after about 5 minutes, those shadows are starting to move on you. And so if you're out there for a half hour capturing something, and let's say you're trying to do some loop closure, so come back where you started, the shadows are not going to be in the same places, and things will start to look funny in the results. And so,
great point.
Go for cloudy while you can. You end up with less bright reflectance and camera issues as you walk in and out of shade, but also your shadows stay. They're more diffuse, so you don't see them as much.
Yeah, no, that's a great point. Yeah, because those shadows they move quick, and that's going to then show up in your reconstruction.
Yeah, I've been told 5 minutes is your window if you like want to get the best, or just come back when it's not sunny like that. Yeah. Or I have a good example. I can probably put on the screen for YouTube here, but I have an example where we captured stockpiles that didn't have a lot of geometry, a lot of texture on them, but they were captured on 2 different days. And so the day where the sun was like directly above, casting no shadows, you almost couldn't tell where the ground and the pile was, versus a day where I don't think it was that much later, but enough that it had some shadows cast, and it was a drone capture, and you could just say like, oh, wow, I can see them because there was some shadows that it grabbed onto.
Yeah.
So it can help.
That's self-shadowing. Like if like you said, if it's a drone looking straight down, if the sun is also directly over above, straight down, you're not going to see any shadows because the sun is in alignment with the camera's perspective. But like I said, as long as you just all of a sudden the sun moves, and with respect to the viewing direction, now you get the shadows. And
okay, so then to wrap this up, we have we've been talking about mainly ground-based capture.
Yeah.
What am I worried about if I want to go capture anything outside from, let's start, there's 2 different, you have aerial and you have satellite. Let's just quickly go over both. Yeah. I'm a drone. What's my tips? Or an airplane pilot who wants to take photos out the side of their window.
Yep. So there again, because I just wanted to get us off the ground and think about other kind of environments. And so so with the aerial, whether that's a drone or an airplane pilot, with a camera, one trick I wanted to highlight, or one caveat, is that in 3D reconstruction, a common and very crucial part of the process is estimating the distortion of the lens. So lenses, that piece of glass in front of the sensor, that lens, is curved. It's made up of many different lens elements that all work together to direct the light of the scene onto the sensor inside of the camera. And so that stack of glass inside of your lens, it usually does the best that it can to give you a nice, perfectly square image, but sometimes you can introduce distortion. You may see terms like barrel distortion or pin cushion distortion, where things end up being a little bit circular, a little, stretched or squashed. Straight lines end up being curved. And so in 3D reconstruction, there is a process by which that lens distortion is estimated and then compensated so that we can remove the effects of lens distortion on that final reconstruction. A problem with it is that lens distortion estimation it's ambiguous, it's degenerate. You can't estimate it correctly when your camera moves in a flat plane looking at a flat scene. And so imagine a drone flying 400 feet above the ground, 100 meters above the ground, looking at a roughly flat ground, like you're flying over a soccer field or a football field. That field is flat. The drone was flying at a constant elevation, looking straight down. You cannot estimate the lens distortion, the radial distortion, that distortion of the lens, and so you're going to end up with a curved, weird result. And so a trick there is just make sure you fly at multiple elevations, or have your camera tilted at a slightly different angle so you're not looking straight down. Tilt it up a little bit. Fly in a few different directions with that camera tilted. Or make sure that the scene that you're capturing has variations in height to it. Or best yet, do a combination of all of that. Fly at a few different elevations with your camera tilted and make sure you're looking at something that has different elevations and isn't just flat ground.
There's a great paper, or not a science paper. It's someone was capturing the indoors. So this is going back inside, but they were saying they found they had much better results when they were taking 20 or like 40 megapixel high-res images, and they were kind of coming at an angle to walls and going around. They found out that they got better results if they didn't capture everything at their head level, that some were at different elevations, and it helped reduce curvature in their model. And it's probably that same problem where they were running into, that distortion, and they found that just taking pictures of like your stomach, your head, even up high, looking down, improved the results dramatically.
Yeah. I think I've said this analogy before, but I treat, computer vision and structural motion and 3D reconstruction almost as if you're building a bridge. You don't build a great bridge. If I'm trying to get from point A to point B, you don't build a great bridge just by putting a bunch of boards end to end in a straight line. Mm-hmm. No, you want a rigid structure with trusses and beams and triangle patterns, and you want a nice web of connectivity to create this nice rigid bridge. It's the same thing with computer vision. If all of my photos that are constant elevation or all my photos are along a single line, you're going to end up with curvature and drift and weird artifacts. You want to have your photos be from different, X, Y, and Z positions. So vary your elevation, move side to side, take from different angles and perspectives, and that's going to give you a solid web of connectivity in your reconstruction and give you that nice good result.
Okay. And so satellites are they exactly the same? You need instead of a cloudy day, you want a clear day.
Yeah, you want a clear day. The one caveat I will say with satellites is, satellites, yes, you look at satellite imagery and it's like, wow, that's a beautiful looking photo. I can see the ground. Everything looks nice and neat. It's a cool photo. But the geometry of how that photo is constructed is totally different than all of the other cameras that you're used to. Satellites do not take just a single photo of the ground. Okay, I should most satellites. Mm-hmm. Most satellites do not take a single photo of the whole ground. They use typically what's called a push broom camera. Some older style ones used a whisk broom. But the idea is the camera leverages the fact that satellite is moving around the Earth. And so instead of trying to capture a big rectangular photo, it captures just a long, really thin photo, like a single line, mm-hmm. of pixels that then as the satellite moves, it sweeps that line of pixels across the Earth's surface and to capture that full photo. So the challenge there for computer vision and 3D reconstruction is that the satellite was moving during that entire process. So instead of assuming that the entire photo was captured at once, that top row of pixels may be from one position, the next row of pixels is from a different satellite position, the third row, the satellite's moved even further, and so you have to compensate for that in your 3D reconstruction algorithms. And so there's some really fancy math to update your camera model to compensate for that, but that's just something to be aware of. Don't assume that you can just take off-the-shelf satellite photos, drop them into structural motion, and get a great result.
Uh,
So there
you,
is some complexity there.
you do have some of that same issue with, let's say, taking drone photos while it's moving as well, because the sensor readout might not be super fast. So
Great point.
if it's moving at 35 miles an hour, taking a photo, by the time it's read out the entire image, if it's not doing a global shutter, you're going to have, what's that called? You get the
rolling shutter effect.
And I know there is a lot of software now. It's like you can apply a rolling shutter correction, and it's still, I would rather you not have it, but it's there to help you get better results. So know that, if you have the time, stop the drone. If you have enough batteries and time's not of the essence, get that sharp, or get a camera that reads out the whole image at once.
Yep.
It'd be better. I remember learning about satellites in college, and I'm a geography major, and we did the geospatial stuff of learning about that. And a lot of those camera sensors actually, by the way, don't even take RGB. They have
the multispectral, hyperspectral stuff.
I was just talking to someone how I remember we were identifying plant species based off of hyperspectral imagery, and I was like, this is the most fascinating thing. But then come to find out, you need a PhD to really learn or to deal with that, which makes sense, right? It's like, well, how many people are going to be getting satellite imagery and doing analysis? But okay, so this is really, really good. I would say, hopefully there's tips here. And then when we talk about this in like 2 or 3 years, we can just say none of that mattered because machine learning and AI has solved all of these issues. I'm already seeing cracks in some of these things. I would say, though, still, any of the ML, AI things to help predict and fix is never as good as getting traditional captures correct in the beginning. They're always saying, this is great. This will help you, recover what you can. But,
there's and just to provide more color from my perspective on that, is machine learning can capture really complex, effects that could be hard to mitigate otherwise. So it is possible. You could say that I'm going to do machine learning based lens distortion estimation because maybe my polygonal model, my geometric model with so many different distortion terms, it can do a good job, but it can't capture that sub-pixel variation that maybe a machine learning model could pick up on. And so there is going to be times when, yes, machine learning is going to be better. There's going to be times machine learning is going to be worse, but then there's always the trade-offs. A common one I think about is power efficiency. Do I want to have a machine learning based pose estimation? That I need a powerful GPU and process that and use all that energy on my mobile device. I don't want to drain my battery. Or would I rather use maybe just a simpler technique, quote unquote, simpler technique that understands the geometry and can generate through 3D construction using engineered and well understood principles? There's trade-offs.
Just a robot that has wheels that are rolling alone. You should know the distance you've traversed based off of the rotations of the wheels. I mean, things like that don't require querying a neural network. I also know that though things might not be the best results, I see there has always been this, for lack of a better word, hyper fixation on the best result possible when sometimes you don't even need close to that. Thinking of a robotics, and I just need to know that there is things in my space I don't want to run into. You might need a very rough 3D model through SLAM that's not perfect, but that all you need is fast and rough. So knowing where that lies is, but I know people.
I'll say it comes back to what I touched on before. Like, computer vision is a tool. You can use it to solve a problem. I can take a structure from motion algorithm and use it to reconstruct so many different environments or use it to power so many different applications. But it's when you have the domain knowledge for that particular application, that's where I feel like the real power is that's where you can make those big improvements by leveraging your understanding of the problem that you're solving. Okay, I'm going to talk about stockpiles because that's what I know and love. But it's because I have thought about stockpiles and outdoor reconstruction for the past 10 years. I know how to optimize the 3D reconstruction algorithm for that environment to make it as fast as possible and at the level of quality that's necessary in order to deliver answers to the customer. I do not need sub-millimeter precision on that 3D pile in order to compute its volume. And so there are sacrifices and pros and cons and design decisions that can be made in order to tailor that very general tool for a specific application. And I think that same mindset is applicable to everything. It's just a tool that then you can optimize for healthcare, for outdoors, for indoors, for aerial, for whatever your environment may be. There's always ways to customize it and figure out how can I best use this tool to get my job done.
Wow, that's a good note to end on. I think a lot of people need to start with what's my goal before they start with how I'm going to capture this. Work your way backwards and optimize. So, well, thanks, Jared. I learned a lot today, and I think that our listeners will as well. There's always two ways to approach everything. There's how do I capture it, or what software or algorithms I use. So, jump into this. There's always forums. There's always research groups out there that are always willing. People like Jared are always on these and answering questions because this is what you love, right, Jared?
I love talking to people. I love always learning about new things and talking through computer vision with people. And absolutely.
I sometimes think that questions will pop up. Oh, what about this? You're like, I've actually never even thought about that, but now that could translate into what I'm working in today. So, always be open-minded to that. So, well, thanks, Jared. If you have tuned into this on podcasts, you can find on any major podcast out there, Spotify, Apple Podcasts, or you can capture this on our YouTube channel on Every Point, where we will be posting episodes every 1 to 2 weeks, depending on how quickly I can get Jared on another episode. So thanks for listening, and thanks for your time, Jared.
Thanks, Jonathan.